maximum vegetation, whereas the deserty looking colors, the browns, represent minimum. So you're not seeing much biomass in the desert, as you'd expect. It's not like there's a lot of trees and stuff there. So 563 billion tons of carbon. Of that, 560 billion tons of it is on land. Only 3 billion tons of it is in the ocean, in terms of the biomass. Compare 750 billion tons in the atmosphere. Biomass in the ocean. So again, not the details, but the relationships between these numbers. So in the open ocean, 0.003 kilograms for every meter squared of water, which represents in a billion tons globally. So it's not very productive, but there's a huge area of open ocean. In contrast, in upwelling areas, places where that cold nutrient-rich water comes up from the bottom, we see that the productivity is 0.02 kilograms per meter squared. Only 8 million tons globally. So it is productive in terms of the ocean biomass, but it's a small area. 30% of the biomass in oceans is actually found in those estuaries we talked about, and 35% in coral reefs and algal beds. Terrestrial biomass. Again, not the details of the numbers, but the relationships between them. Productivity in the rainforest, 42 kilograms for every meter squared. Ocean, 0.003 kilograms for every meter squared. That's a huge difference. Oops, sorry. We're back to terrestrial biomass. So 42 kilograms per meter squared in the rainforest. That is about 460 billion tons globally. 43% of the total terrestrial biomass are actually found in the tropical rainforest. So of all the terrestrial or land biomass on Earth, almost half of it is found in the tropical rainforest. 0.06 kilograms per meter squared in deserts. That's 480 million tons of carbon. So if you look back at the most productive areas of the ocean, the upwelling areas, 0.02 kilograms per meter squared. The terrestrial, 0.06 kilograms per meter squared in the deserts. So, biomes, the net primary productivity. What does net primary productivity mean? Well, that is the new biomass produced per time, per year. So, net primary productivity in marine biomes, 2,500 to 125 grams per meter squared per year. About 76% of that's in the open ocean. The net primary productivity of terrestrial biomes is 4,000 to 10 grams per meter squared per year. 49 billion tons per year by forests, 50 million tons per year in deserts. On average, terrestrial productivity is 6 times greater than marine productivity. The average residence time of carbon in land vegetation is 10 years, whereas in marine phytoplankton it's 26 days. We talked before about residence time and how long something tends to stay in a reservoir. So in the land vegetation reservoir, we see that carbon stays for about 10 years. In the marine phytoplankton reservoir, we see that carbon only stays for about 26 days. So which one's cycling faster? Well, the marine phytoplankton is cycling carbon through a lot faster. So there's an animation that you should watch on your video. So we're looking at zooplankton in blue, phytoplankton in green, and sunlight in orange, and nutrients in purple. So let's see what happens over time. So you see that as you go from January into the spring, you're having an increase in phytoplankton and zooplankton and sunlight. Your nutrients are going down because these guys are using it to grow. So there's a big spring bloom when there's lots of them. Then you're going through the summer where there's less. And the sunlight is coming to a maximum and decreasing as you come into the fall. But you're having another bloom, a fall bloom, of these phytoplankton and zooplankton guys. And your nutrients are going back up because there's less of these guys to use those nutrients. there's some phytoplankton, diatoms, coccoliths, dinoflagellate, coccolithopores. These are shown many hundreds of times their actual size. Okay, so let's look at some zooplankton. Examples, copepods. These are shown many times their actual size. So if you want to look at the world productivity map, there you go. We've already seen that. Oops. Okay. So the examinable readings for the biosphere and ecosphere would be Chapter 5, pages 135 to 169. However, don't include Box 5.1 or Box 5.2 or Table 5.6. The only animation was the mid-latitude productivity. Do have a look at that. Understand the spring bloom and the fall bloom, and how the nutrient levels and the sunlight levels compare with how many phytoplankton and zooplankton you have. So now we're going to do a mini review for the midterm test. The test is held during next class, and again, it is not held in the lecture hall, so pay attention to that. Okay, a lot of people have come and asked me about the chart here. So, excuse me, it's looking at igneous rocks, firstly, igneous rocks. So those ones that form from the cooling of magma. The intrusive ones cool inside the crust, things like gabbro, diorite, granodiorite, granite, and alkali granite. Those cool in the crust. So you have to try to remember, do those have big crystals or little crystals? Well, they have big crystals because they cool slowly inside the crust. Extrusive igneous rocks have the exact same composition, the exact same minerals as these intrusive ones, but they cool outside of the crust. So things like basalt and rhyolite. So if you look on this axis, the y-axis, we have volume of minerals. Go from 0%, so none of it, 25, 50, 75, up to 100%. As you go from left to right, you're seeing more silica content in the rock. So would you have more silica in rhyolite or basalt? You'd have more silica in rhyolite because it's further along the x-axis. It has more silica content. So when you look at these charts, you have to divide them up and figure it out. So for instance, we're going to do granite. So I've divided it up. This particular granite has approximately 30% quartz. How did I figure that out? Well, here's the quartz line. So if we find the place where the quartz line meets our granite, and we move across, it's about 30%. Okay. Then we want to figure out how much of our granite is made up of these alkali feldspars. So we have to start at our 30 line, and then we go up to the point where the alkali feldspar line crosses our granite, and we move across and read there. So we find that that's about 74. So 74 minus the 30 is 44. So about 44% of our granite is made up of these alkali feldspars. Then we want to find out how much of the granite is made up of plagioclase feldspar. So we start at our 74 line, and we go up here to the point where our plagioclase feldspar line crosses our granite, and that is right here at about 89. So 89 minus the 74 leaves us with about 15% plagioclase feldspar. Then, if we move up and do it for the amphiboles, we want to find out how many amphiboles we would find in granite, in this particular granite. We could start at the 89 and go up to right up to the 100. We have about 11% amphiboles. So the granite we have is mostly alkali feldspar, then quartz, then plagioclase feldspar, and then some amphiboles. So the major component of our granite that we chose is alkali feldspar, quartz, then plag, then amphiboles. It must total 100. If you see this diagram on the test and you're